Well, good morning. This is 8:39. Sorry, we're 9 minutes late getting started. But I was grading papers, and when I realized it was time for class, went down the hall and found out a biology class was locked out of the classroom, and the police hadn't shown up. So I had to go down looking for the police, found him, and get him to come up and unlock the door for him. So that took me extra time. So sorry we're late getting started. But then, too, I'm the only one in the room. So hopefully some students will be showing up soon. I'll wait and hold off on announcements until at least I get a student here. So let's start from the current slide here, if it'll open. I don't know how it's on the receiving end. On my end, my screen is flashing, dim, bright, dim, bright. The power seems fine, but my battery went all day yesterday red and never charged. I had the computer on from more earlier than 8:30 in the morning until after, I'm guessing 6:45 last evening. The red light stayed on all day long. I don't know what's going on with the battery, but anyway, hopefully this is recording adequately. All right, and since no one's here, we'll pick up where we left off last time. Last time we talked about what the definition is between linear dependence and linear independence. If you have a set of functions, however many you have, 2, 7, 14, 85, whatever, a set of functions, they're linearly dependent on an interval I if there exists some constants, C1, C2, up to however many you have, 2, 5, 7, whatever, and those constants are not all zero, so that if you multiply C1 by F1, C2 by F2, C3 by F3, add all those multiples together, and you can find that's equal to 0 for every x in the interval, okay, then the set is linearly dependent. If you have a set of functions that you cannot find a set of zero, constant c, that when you multiply them by the function, c1 times f1 plus c1 times c2 times f2 plus c3 times f3, so on, you cannot find the c's except if all those c's are zero, then that's linearly independent. We've got a student. All right, good deal.
I'm going to be here.
Huh?
I couldn't leave you.
Yeah, at some point anyway.
I got the test for you.
What's that?
I got my top 3 tests.
Oh, good deal. Go back and I'll use the beam. Today is probably
Now, if I'm correct, you said don't do the first 6.
yeah, you don't need to, right.
And this ain't my work for like these, but
That
I watched your
there's
video.
not much you can do yourself. Stay what you want.
I got that off the video. One of them I was confused. Is this one? I don't know if that's the correct way.
It looks right.
Okay. Because I saw your video, and you had like 1 sheet or 2 sheets.
Right.
And then this one was like, ah.
Okay. Using almost staples. Not using them well at that.
Okay, I tried. I'm gonna write my name on this one. I'm sorry that this thing.
No problem.
This thing was.
It's a fussy thing. What I'm going to do is put them inside here.
See? You're smarter than me.
Oh, no, don't give me that much credit. All right. Okay. All right, the couple of announcements. One you've heard. Have you done the student course evaluations?
Not yet.
Not yet. Well, you got plenty of time. Just don't forget to do it.
Yes, sir.
Okay, good deal. The other thing is, this has been happening for several weeks now, and I haven't been announcing it because I never knew for sure if it was going to happen or not. But on my syllabus, locator card, everything else, I say I have office hours on Tuesdays and Thursdays here from 10:45 when this class is over with until 4:30 when I needed to leave to go to the Birmingham East Campus to teach a physics class. Well, for the last several, both Tuesdays and Thursdays, I've been trying to get a variety of things done, most of which were the signatures on meeting with my instructors to get their signatures on their evaluations. And it seems like none can all meet at the same time. So I've been over there just about every Tuesday and Thursday afternoon for the last several weeks. I've got to go again today, hopefully to pick up my last instructor who was out last week and doing something else the weeks before. So I hope to get him today. I don't know what time yet. And then on Thursday, I know we've got a meeting. I believe it's going to be 2:30, so I'll be leaving here around 2 o'clock and won't be back. And then next Tuesday, we have a hearing, and I can't remember the time of that, but I'll be leaving sometime well before 4:30. So today, Thursday, and Tuesday of next week, I know I'll be leaving this campus earlier, and I'll be over on the Birmingham campus. And after Tuesday, though, I'm hoping, knock on wood, that I won't have to make those early trips over there.
So basically no office hours this week?
So yeah, no, I have them, but I won't. I'll be leaving sometime, possibly as early as 2, no earlier than 2. So I have office hours up until 2. I may have them later than that. It just depends on when I can schedule to meet with the instructors. Like one time last week, it was 3 o'clock, so I left here at 2:30. So it just varies on when I can catch the various instructors over there. So it's been crazy, and it'll continue being weird until next Tuesday. That'll be the last one, I think. After that, I'll be back here, but we don't have much term left. Okay.
Yeah, what was I ask? What day is our final? Because I got my chemistry teacher. She's going on vacation early, so she decided to cancel like her final and make our last test like a final.
Right.
So our last day is like the Wednesday, I think maybe the 24th, 29th.
Wow.
I think it's the 29th.
Okay. Yeah. That's a Monday, isn't it? Or Wednesday.
So.
Right. Okay. Well, the last day for this class is the next day, the 30th, whatever day of the week that is. It's a Tuesday or Thursday, I know, but I don't know which one it is. And on that day, I will give you your final exam, and it's due whenever you can get it back to me. And the previous, on the calculus, I'll give you that final, or give them the final on the previous day, Monday, or Wednesday, whichever it is, the 29th. And then there's, that's due within a week, So final exam, we don't have a week for finals in the summer. We just have the last class period is that. So
is the final going to be cumulative?
Is it cumulative? No.
It's just going to be the last.
It's going to be the last test, sort of like the chemistry.
You're a great man.
Oh, no.
I hate it. Is it comprehensive? Is that what it is?
Yeah, well, both means the same. Yeah, or I count them being the same. No, it's going to be the last test, just like your chemistry is going to be. Whatever your last test is, your final test, final exam. Okay, so let me get things set up here. I had some problem with my projection yesterday, but it stood up and I find that the wrap.
It's good you got your reading glasses today.
What's that?
You got your glasses today.
Yes, I did remember doing that today. And it's a little easier to read. And as I said before, yesterday I had the computer plugged in up here from before 8:30 in the morning until probably after 6:45 yesterday evening. and the battery light never changed from being red. So I don't know, my battery may be going out. It's been charging the whole time, but the lights sort of flash and dim and stuff, so I don't think it's doing a good charge. But it seems to be working, so if you can't see it at home, that may be the issue. All right, now last time we talked and introduced linear dependence and linear independence, okay? You remember enough about what that was to do the example? Or do I need a little review?
Maybe.
Yeah, I thought, okay. All right, if you have a set of functions, however many you got, 2, 7, 15, whatever, set of functions, okay? Now, if you can find any constants, okay? Let's say we have functions, how many functions you want to have? 2? That's really easy. 5, okay. 4, okay, 4. They have 4 functions, F1, F2, F3, and F4, okay? Now, if you can come up with a C to go with each one, C1 times F1, plus C2 times F2, plus C3 times F3, plus C4 times F4, and however many you got. If you can come up with a constant, multiply by each one of those. It's not the same constant, okay? Any old constant for any one of them. Not all of those constants can be 0. But if you can come up with that combination and you add those together, if you can get it to come out equals 0 for every value of x in that interval on which those functions are defined, then that's linearly dependent. In other words, one or more of those functions depends on the other. Okay? Now, if you can't, if the only set of c's that will add up that way to give you 0, that means they're linearly independent. Okay? And we did the example. A straight line like that, and then the absolute value function, they're independent of each other. You can't get a linear combination of absolute value functions with the identity function that'll ever give you 0 for all the values of x in their domain. So those are linearly independent. But if you have this function here and this function here, all you do is multiply one of those by a constant and you get the same function. So, and that constant can't be 0. So let's try doing that with this set of functions. Okay? Here's your f1 of x. Let me get my pen set up. Can't get it. There it goes. f1 of x is equal to cosine squared x. Pretty exciting, huh? f2 of x is equal to sine squared x. f3 of x is equal to secant squared x. Second. And f4 of x is equal to tangent squared x. Okay. Now, there's a set of functions. Our interval of interest is going to be on minus pi halves to pi halves. Okay. Now, one reason it has to be on that is that secant and tangent are both defined on that interval, but not beyond it. You cannot take the tangent or secant of minus pi halves or pi halves. So you have to be within that interval for those to make any sense, because they go to infinity there, remember? Okay. So sine and cosine are defined everywhere, so that's not an issue for that one. So there's our interval.
Wait, is it the reason why they don't work is because like tan is sine over cosine? You don't have to, if you put like pi halves for cosine of be 0.
I think what you're thinking is right. I'm not sure what you said it was right, but the thinking was right. is that secant is 1 over cosine, and tangent is sine over cosine. So both of them have cosine in the denominator, and cosines are 0 at negative pi halves and pi halves.
Yes.
Yes, yeah. That's exactly why they're not defined. Yeah, perfect.
And then if you go pi, it would be 0 too, right?
So again,
You couldn't put pi either. It would have to be like,
you could go between pi halves and 3 halves pi's, and that would be fine too.
yeah.
But you could include pi then. But you can't include pi with something to the left of minus pi.
Basically, it doesn't work on the cross, it works up here.
Yeah, exactly. You got it. Yeah. But it actually works from here to there.
Oh.
Yeah. Or from here to there. But it doesn't work there or there.
Not a full circle, a half circle.
Half circles, right. Yeah. And they're the split vertically. Yeah.
I'm on board.
Yes, good deal. Okay, welcome aboard. Okay, all right. Now, so we want to know if these are linearly dependent or not. Okay? Now, I think if you thought about it really hard, you could see that they're linearly dependent. Because let me suggest to you, because of this, that cosine squared x plus sine squared x is equal to what?
That's
1. You got it. Okay? Now, maybe thinking a little harder here.
So can we say F1 plus F2 equals 1?
Yeah. 1 times F1 plus 1 times F2 is equal to 1. Now, that doesn't make them linearly dependent, but just the fact that's true, right? Now, over here, for these two, I think you probably realize that one...
It's, I know this one. Tan squared equals 1 minus secant.
I think you're right. Let's see if that's right. Tangent squared, no, secant squared minus 1. Okay. Because tangent squared plus 1 equals secant squared. So tangent squared is equal to secant squared minus 1. Okay? So therefore, tangent squared x minus secant squared
Equals what?
x equal, well, wait, wrong. Other way. Well, equal minus 1, right?
Yeah, I didn't.
Okay? Now, what that means is that cosine squared x plus sine squared x plus plus tangent squared x minus secant squared x is equal to what?
It'd be 0.
Yes, is equal to 0. And not all of these coefficients are equal to 0. Certainly if you put 0 plus 0 plus 0 plus 0, that would be 0. But here we came up with a set of coefficients, C1 equal 1, C2 equal 1, C3 equal 1, and C4 equals minus 1, and we came up with a combination that gave us 0, so this is therefore linearly dependent. Because there is a set of coefficients, C1 through C4, not all 0, that when you combine those with these, add them together, you can come up with 0. So these are linearly dependent. Okay? And they chose exactly the same ones we did. Okay? C1, C2 equal 1, C3, well, they put their secant squared first. And I guess they named them that way, so yeah, we probably should have 2. But it doesn't matter the order you do them. So yes, they're linearly, they make that equals 0. Now, a set of n functions, f sub 1 of x, f sub 2 of x, all the way up to f sub n of x, is linearly dependent on an interval I if at least one of the functions can be expressed as a linear combination of the remaining functions. Because if all those are equal to 0, right, like this one, you could say that secant squared x is equal to cosine squared x plus sine squared x plus tangent squared x, right? Because just move it to the other side. So you see, this one depends on the others. They're linearly dependent on each other. If that's true, if you can come up with some combination, linear combination, where all the coefficients are not 0, but the series is 0, for all values x in the domain, on the interval, then it's going to be true that at least one of those can be written as a combination of the other two, so therefore we say secant squared is dependent on the other. So it's linearly dependent. So that's why we phrase it that way. Okay? All right, I don't see any reason to beat that any more to death. So let's go to, all right, to erase. Example 6. Here's a set of functions. f1 of x is equal to the square root of x plus 5, and that 5 is outside the square root symbol. f2 of x is equal to square root of x plus 5x, and the 5x is outside the square root. f3 of x is equal to x minus 1, and f4 of x is equal to x squared. Okay. Now, we're going to restrict ourselves to the interval 0 to infinity. Okay? Now, there really is no reason not to have a bracket in front of the 0. Because 0 could be included. No problem with 0 being included. Negative 1 couldn't be included. Why?
Because the square root.
Square root, you can't make the square root of a negative number. Because we're on the real number system. Okay? So, you could include 0, but they chose not to. It's not a big deal. It's just one number. And there isn't any value at all. Okay. So, what we're going to know is this set of functions, 4 functions here, linearly independent or dependent. Okay? Now, the last one, just because we knew our trig identities, we could come up with the answer, just looking at them. This one, there's no real clear identity here. So here's the general way you can do it. Takes a little more time, but let's see if we can do it. Let's come up with a C1. C1 times F1, the square root of x plus 5, plus C2 times F2, which is the square root of x plus 5x, plus C3 times x minus 1 plus C4 times x squared. Okay? And see, can we make that 0 without all those c's being 0? Okay? Now, multiply through and you got C1 root x. Okay? I really want to put it the other way, but we'll leave it that way. Plus 5C1 plus C2 root x plus 5xC2, okay, plus C3x minus C3 plus C4 x squared equals 0. All right. Now, let's combine the terms that have similar powers of x. So this says that C1 plus C2 has to be equal to 0, right? It also says that C1 has to equal 0 because that's the only, nope, wrong. Okay, sorry about that. Okay, here we have a constant, and here we have a constant. So this says that 5C1 minus C3 is also equal to 0, right? Okay. And here we have the x terms here says that 5x minus, no, plus 5x C2, goodness, I can't write, plus x times C3, that's got to equal to 0. And then finally we have that C4 has got to equal 0. Well, guess what? C4 is not linearly dependent on any of these others, okay? So it's out of the picture. It is independent, okay, of the others, but are the rest of the set. Okay, well, what we have here is a matrix, okay, you might say, and in these variables. So let's say 1, if these are your C1s, these are your C2s, here are your C3s. We already thrown C4 out, okay? So 1, 1, and here's your product, 0. So basically, it's saying C1 plus C2 is equal to 0. 5C1, I'm leaving off the C1s. 5C1 minus C3 has to equal to 0. And you can divide out the x's and just have 5C2 plus C3, that's equal to 0. Okay. Now, this is 3 equations, 3 unknowns. Okay. What's that?
I'm really lost right now on this.
Okay. Okay, have you done any matrix algebra at all?
I don't think so.
Okay, all right. So let's go back to okay. All right, I was trying to do it that way because it's a little easier. So let's just call this as C1 plus C2 is equal to 0. 5C1 minus C3 is equal to 0. That's the same thing we have here. And the only thing I've done is take out the x's, divide them out, and 5C2.
Are you basing that little chart?
I was going to do it into a matrix, but since you haven't had matrix algebra, then okay. No, plus C3. Now, we're going to do the same thing I was going to do, but we're going to just do it a little differently. Okay. Now, what I'm wanting to do is to eliminate this. You remember the thing, elimination by addition, when you have a system of equations? You don't. Okay. Well, I'll show you how it works. If we multiply this equation by minus 5, it's still the same equation, isn't it?
Yes.
Okay. So let's do that. That'll be a minus 5C1. I'm not going to leave it in front. I'm going to actually multiply it. Okay. And this will be minus 5C2.
That just gives us 0 on everything. We do that.
Wait, yeah, let's just hang on. And that'll be a 0, right? Now let's add these two equations together, and that gives us
0.
Yeah, just these two together. That gives us 0. We get minus 5C2 is equal to 0. So that means C2 is also equal to 0. Okay?
Wouldn't C2 equal 0 though? Because minus 5 C2 and then that.
Oh, wait, I'm sorry. Yeah, no. Minus 5C2 minus C3 is equal to 0. Sorry.
Wouldn't those go to 0 too?
Say again?
Wouldn't those two go to 0?
Okay. Any reason why?
Well,
Okay.
the negative 5 C1 was 0 because negative 5 over 5 is 0.
Okay, we don't know anything about C2, 1, we just eliminate it, okay, by multiplying that row by minus 5. So this adds a 0. This, just doing these two. Now we got minus 5C2 minus C3 is equal to 0, okay, right? Now, with this equation, that 5, is that what you're saying? If you add these two together,
Yeah.
you get everything wipes out too. That's bizarre, isn't it? Okay. And so you get all zeros there. But then you
aren't we supposed to write an X though for that?
What's that again?
Is there supposed to be an X?
Yeah, I took out the x's because I just divided them away.
That's
We're only concerned with the coefficients.
That's fine.
Yeah. Okay. So now when you add these two equations, where was it? Yeah. Add these two equations, you get this one. Okay. And you've eliminated these. Then now when you add these two equations, you eliminate everything. Okay? But you got C1, C4 is equal to 0, C2 is equal to 0, and C3. No, I'm sorry, you can't say that. You just have, you've lost all meaning. Okay? But you still have, this is going really poorly, isn't it? If we had started differently, let's go back and try something different. Because you just basically have wiped out your meaning of everything.
I'm sorry.
No, it's not your fault. It was my choice. And I just think I must have chosen badly. Okay. These are the three equations. Okay. Make sure I didn't copy a problem down wrong. Nope, that's right. If we had started off with these two equations, let's do that. It may be I'm just showing exactly what I need to show. If you add these two equations together, you get 5C1 plus 5C2. These two add to 0. That's equal to 0. And then, yeah. What this is telling you, there's an infinite number of choices for C1 and C2 that will make this equal to, that make these things equal to 0. it doesn't matter. It's really easy to make this equal 0. Can't do anything with C4. That's got to be 0. But if you had anything else, let's just, well, it's easy to do if it's in a matrix, but if you have C1 is equal to, say, just pick something like +1. C2 then would need to be -1, right?
Yep.
Okay. So then if you have C1 is +1, this would be 5. That means C3 must be a 5. Okay. And then -1 here would be -5 plus, yeah. So there was a choice. We just randomly chose a 1, and that made this a -1. That made this a 5. Okay? And now with this being a -1, yeah, you get -1 plus a -5 plus 5 is equal to 0. There is a set of C1, C2, and C3 that make that series add to 0, but they're not all zeros. The C4 has to be 0. There's no choice there. But these three, there's a bunch of things you could choose. So basically, what we were seeing was it didn't matter what your C1 and well, they're related to each other, but there are many choices. There's an infinite number of choices for C1, C2, and C3 that could make that equal 0 without all of them being 0. So that is exactly what we're trying to show. When we showed it, I just didn't recognize we were doing it. Okay, so that's just one example. A 1, -1, and 5. That works, but there's an infinite number that do. Okay, and they use 1, 5, and 0. That also, well, the 0 also works for whatever. 0 for C4. And that happens for every x on the interval. Okay? Now, this is a little awkward trying to do this, especially if you have a whole bunch of functions to do. So here's what we do. We're primarily interested in linear independent solutions, linearly independent functions, or to be more to the point, linearly independent solutions of a linear differential equation. Although we could always appeal directly to the definition, which then you have to go around and look and see if you found them all, that's pretty bad. We could also, it turns out that the question of whether a set is homogeneous, of a homogeneous linear nth order differential equation is linear dependent, can be settled somewhat mechanically by using a determinant. Now, have you ever used determinants? Okay. So I'm going to have to show you that one. And
it's basically all we're doing to problems like these, and we're just kind of, we'll do the same procedure, basically make constants out of them.
well, yeah, well, basically it's trying to find a set of constants that will make all of them equal to 0 without all the constants being 0. If you can do that, they're dependent.
And you got those three equations. You got that C1 plus C2 because you took C1 square root of x plus C2 square root of x, and you took the square root of x out of it, right?
Yeah, if you can manage a way to do that, yeah, that without all of them being 0. But that's sort of tedious. Certainly with just 4 equations here, that got to be a little tedious. Here's a way you can do it no matter what. Now I'm going to have to teach you a little bit about determinants first. All right, to erase this?
Yes, sir.
Okay. It's called the Wronskian, okay? Named after Joseph Maria Hone Wronski. A good Irish name, don't you? No, I'm sorry, Polish name. Okay, he was a philosopher and mathematician way back, about the time shortly after our independence. 1778 was when he was born back in Poland, so he didn't care about our independence up until 1853. But here's what he came up with. Suppose you have a set of functions, f1 of x, f2 of x, f3 of x, all the way up to and including f sub n of x, where n is some finite number. It could be 4, it could be 15, it could be whatever. Okay? Now, all of these have to possess at least n minus 1 derivatives. Okay? Must possess at least n minus 1 derivatives. Okay? Now what the Wronskian is, it's called w, and it's a function of these functions. F sub 1, F sub 2, F sub 3, dot, 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 up to and including F sub n. The Wronskian of this set of functions is F1, F2, F3, dot, 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 up to F sub n. You just list them on the first row, all the functions there. The second row, F prime, F1 prime, F2 prime, F3 prime, dot, 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 up to F sub n prime. The first derivatives of each of those. And F sub 1 double prime, F sub 2 double prime, F sub 3 double prime, dot, 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 including F sub n double prime. Okay? And then you can continue taking derivatives of all those until you get down to the F sub 1 to the n minus 1 derivative. Okay? And F sub 2, it's n minus first derivative. F sub 3, it's n minus first derivative. And all the way over to F sub n, and it's n minus first derivative. Okay? And you take a determinant of those things. Now that can be a real pain in the neck, but it's a generally an easier way to do it than what we've been doing. Okay? Now I'll have to show you how to do a determinant. I don't want to do it with this many because we don't have an exact number here. I'll do it with a good size number. Okay? Now, that's what the Wronskian is. It's the determinant of these things. And here's what the theorem states. Now, I'm going to see if I can squeeze it in at the bottom. Okay? Now, I don't know why they didn't start with y's while they started with f's. And now they're going to y's. But it's the same thing. Y1 corresponds to F1. Okay? It's the independent. So here's what the theorems say. Let y1, y2, y3, dot, 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 up to and including y sub n be n solutions of the homogeneous or homogeneous, okay, nth order, linear, nth order, differential equation. I'm just going to call that a DE, differential equation, on an interval I, some interval I. Now, the set of solutions, those n solutions there, is linearly independent, okay, on I, if and only if, that's the symbol for if and only if. The Wronskian, this thing right up here, the Wronskian of y1, now why they didn't call them y1s before, they called them okay, y1, y2, y3, dot, 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 up to and including y sub n, if that Wronskian is not equal to 0 for every x in the interval. I can't write. Okay. It's supposed to be every, and it just kept being anything else but every. Okay. Yuck! Okay. All right. Got too many Y's there. Okay. For every X in the interval. Okay. Now, all this is blah, blah, blah until you actually see it done, right? Is this making any sense to you right now as is?
It's all theoretical,
right.
I can tell, but
right.
I think I'll get more and more if I see an example.
Right. Okay, so let's do it. But see, what you're going to do is take a Wronskian, and I'll go back over how to do that. It's taking a determinant. And if that determinant is anything other than 0, then it's linearly independent. If it is equal to 0, it's linearly dependent. Okay? That set of solutions. Okay? Now, they give, without being an example, they give it for example, okay? So let's do it there. We're going to start really easy and just do 2. Here's your Y1. But they don't pick a very, they pick a pretty interesting one. Cosine of 2 log x over x cubed. Isn't that a fun one? And your y2 of x is equal to sine of 2 log x, okay, over x cubed. Okay. Can you think of any more?
You could rewrite that as, no you can't.
What's that?
Ignore me. I was thinking of something.
Yeah. Yeah. I'm used to ignoring. Second?
I noticed on that Cal 3 test, one of them had a the law of logarithms.
Uh-huh. Good stuff, huh, Maynard? Okay.
ln of A minus ln of B equals ln of A over B.
Exactly. Exactly. Okay, and you'd pick that up in here, right? Or refresh yourself in here. Okay. Now, they say these two functions here are solutions they have and solutions, I think they mean are solutions, of this differential equation, x squared y double prime plus 7xy prime plus 13y equals 0. Okay. Now, on the interval 0 to infinity. Anyone, you want to hazard a guess of why it has to be 0 to infinity?
Because ln?
ln cannot be, you can't take the log of 0, you can't take the log of a negative number. This one has to be an open parentheses there for that, if this is indeed a solution. Now, unfortunately, I think what we have to do if we're going to verify this, do you feel like verifying it, or you want to take your word for it?
Part of me wants to say I want to take your word for it, but I know you won't.
No, it doesn't. I have no wants here. It's just whether you feel like you need to verify it or not.
I believe you.
Okay. All right. We're going to say that's true. Okay. Let's see if the book says verify. Okay. No, they don't. Okay. Now they do say this. Note that the coefficient function a1 of x, which would be x squared, a2 of x, which would be 7x, and a3 of x, which is just 13, are all continuous functions on this interval that we've chosen, the a sub 2 of x is not equal to 0 because we left the 0 out. So it will never be 0, okay? So it seems to fit the bill, okay? For every x in the interval.
No,
So what?
When we say from 0 to infinity, when we plug in 0 or we plug in like 1?
Well, what do you mean plug in? You can't plug in 0 because that's not included, okay? The open parenthesis says you don't include 0. If that was a bracket, you did include 0. And this wouldn't work there because, number 1, the logs, but number 2, this would be 0 and that would be 0, then you have 13y is equal to 0, so y would be 0. That wouldn't be a very interesting function, right?
Would there be a bracket on infinity then?
No, infinity is not a number. It keeps going, so you never bracket either negative or positive infinity. There's always parentheses. Okay? Numbers can be bracketed or not. And this one, 0 is not bracketed. Okay. So, we're taking the word that those are solutions. So what we have to do is come up with a Wronskian for these two functions to see if they are linearly independent or not. Okay? So, the Wronskian of these two, y1 and y2, if you remember what it is, it's the determinant of the functions cosine of 2 log x over x cubed sine of 2 log x over x cubed. That's the easy part. The first row is just those two functions. Yeah, because you got to take the derivative of those two functions. So let's do that. y1 prime of x is equal to what? Yeah, unless you wanted to write this as x to the minus 3. Okay, quotient rule's fine.
I forgot, is it low d high?
Yes, it is.
Low
is x cubed. Derivative of the numerator is?
You gotta do product rule.
That's not a product rule, that's a chain rule.
Oh, that's chain rule? So it'd be negative sine of 2 log x. Okay, no, okay. Now do what you're trying to do. 2 over x.
2 over x times 2 over x. Okay?
So it'd be negative.
Okay. Second?
No.
Okay. Now that's just the first. That's the low D high. I probably should put brackets here rather than parentheses. Okay?
Alright, the next part, it's going to be 3x squared times cosine.
Oh, okay, okay. 3x squared, yeah.
Times cosine 2 ln x.
Cosine of 2 ln x.
Over, and then that whole thing to the x to the 5th.
X to the 6th.
Oh, that's 6.
Because you square x cubed.
Yeah, wait.
Remember, over low squared. Okay. Now,
Can we simplify it a little bit though?
what's that?
Could we simplify?
Yes, I was just going to say, let's see if we can simplify this thing a little bit.
We get rid of the 2 over x and it becomes negative 2 sine. Or,
Okay, you can get rid of the over x here with one of those and make it a squared.
yeah.
Okay? And that means you can take out 2 of these and make it to the 4th and get rid of the x squared there and the x squared there. And I think you've got it then. So this is going to be, like you said, minus 2 sine of 2 log x minus 3 cosine of 2 log x. All over x to the 4th. Okay, so there's your y1 prime. That's what we're going to put here. Minus 2 sine of 2 log x.
Why does the x squared go away though?
Well, because you had an x6 in the denominator.
Yeah.
You had an x squared here, and well, first you had an x and an x cubed here, so that made it x squared, right? 1 over x here, x cubed here. So you have an x squared up here, you have an x squared there, right? Okay, so the x squareds could be factored out, and then they could eliminate 2 of the x's in the denominator, giving you x.
Could we make it negative 2 sine?
Yeah, that's what we did. Minus 2 sine.
Oh, I didn't see that. I'm so sorry.
Yeah. And then the minus 3 cosine.
I was looking to the left, not the right side.
Okay. So, there's what this is becoming. Minus 3 cosine 2 log x over x to the 4th. Okay? We also need to do our y2 prime. So I'm going to have to do it down here. I don't have room up there. y2 prime. And that would be what? Yuck! There it came back. It's just doing weird things.
I'm just going to guess. It's just a guess. It's going to be 2 cosine 2 ln x minus 3 sine 2 ln x over x to the 4th.
Let's see. Yeah. Is that what you said?
Yep.
Okay.
Is that right?
I'll buy that. Okay.
Now, I didn't work it out. I just kind of.
Yeah.
Okay.
Yeah. And that's not a bad idea when you can see a pattern and the pattern works and you're not making a dumb error with it. And my looking at that thinks you're probably right. I don't see any problem with that line of reasoning. So I believe you're okay. Now, a 2 by 2 determinant is a very easy thing to do. What you do is multiply downward here. Okay? Got it? Multiply downward there, and then multiply upward here, but you negate the upward. Okay? It's the product. Okay. If this were A, B, C, D, you're taking the determinant. Here's what it is. AD minus BC.
It's just like doing, I mean, that's exactly like cross product.
Yes, because that's done by the determinant.
So we would do cosine 2 ln x over x cubed times 2 cosine 2 ln x, and basically we could just say it would be 2 cosine squared.
2 cosine squared of 2 ln x minus 3 sine of 2 ln x cosine of 2 ln x. Okay? All that's over x to the 7th, right?
Yes, sir.
Okay? Okay? Then it's minus. I'm going to try to condense that a little bit, because I don't have enough room to write it as leisurely as I did this last one. Okay? That's going to be minus a minus, so that's going to be a plus, because that bottom was minus, 2 sine squared 2 ln x got a cold coming on, or?
Yeah.
I'm sorry. Plus 3 sine of 2 ln x cosine of
Now, why
2.
is it? Oh, I know why.
Okay? And that's also over x to the 7th. Okay? Now, when you go to add these two things together, don't you see that this one and that one will add to 0? I'll wait. Don't rush. Because we have the same denominators.
That wouldn't go to 0. They just.
Huh?
You have 2 cosine ln x.
This is the minus 3 sine.
Oh yeah, those go to 0.
And
Yeah,
plus
I agree with that. I was saying,
those two go to 0.
isn't your final answer just going to be 2 over x to the 7th?
Is what? You're absolutely right. You're absolutely right. And this comes up 2 over x to the 7th. And that is never 0 anywhere in your domain. Ever. So therefore, the Wronskian is not equal to 0. These two functions are linearly independent. Right?
Yes, sir.
All right. Now, let's see. Now, it said, rather than expanding this unwieldy determinant, let's just choose x equal 1 on the interval. And then they just did a lot simpler one. We did the unwieldy, and we came out in good shape for it.
Is there a drink machine?
A what?
Is there a drink machine?
Yeah. It's probably not a bad time to take a break, is it? Okay, let's take one. You want me to leave this up here or not?
We can pause it.
It doesn't matter. I can leave it or not.
I have it all written.
You have it. Okay, well, I'll go on and delete it. And then I'm going to put this on what?
I've had a rough week with just studying.
Oh, I see.
So.
It didn't hurt to have a little break. All right, so we just did the Wronskian for just a 2x2 system, and we'll do that. They took the easy road out and first did the functions evaluated at 1 and saw the Wronskian was 2, which is exactly what it would have been because we had 2 over x to the 7th. If x equal 1, that would have been 2. So they were right. But the deal is it wasn't 0. If the Wronskian had come out being 0, they would have been linearly dependent functions. Since it came out other than 0, they were linearly independent. So a set of n linearly independent solutions of a homogeneous or homogeneous linear nth order differential equation is given a special name, and here is its special name. Fred. No, I'm sorry. Any set goodness gracious. Set.
Soy.
Second?
Did you write soy?
No, I was going to write set y, and I just left off the t and started writing the y. Okay, I don't know what's wrong with that.
It looks like S theta T.
What's that?
That looks like S theta T.
That's the way I would make fun of my writing. You lose 15 points for today's class participation. Okay, never mind. Huh?
Go ahead and take another 20.
Okay. All right. Any set y1, y2, y3, ... up to and including y sub n of n linearly independent solutions. That's a pretty big abbreviation. Of the homogeneous or homogeneous nth linear nth order differential equations, okay, on an interval I is said to be a fundamental set of solutions. That's the big name. Fundamental set of solutions. Okay. On that interval. Okay. Now, the basic question of whether a fundamental set exists for a linear operation is answered in the next theorem. That's the definition. Here's the next theorem. There does exist a fundamental set. I'm going to abbreviate that, fundamental set of solutions. Okay, for the homogeneous or homogeneous. Okay, that's going to be abbreviated that way. Linear, nth order, differential equation on I, on some interval I. There exists a fundamental set. Now, as I was writing that, it was coming to mind. I don't know if this is worth saying or not. The linearly independent set of solutions has absolutely nothing to do with the thing of it being a linear differential equation. Linear differential equation, that means none of the y's or y primes or any of them are squared, half power, anything else, cross product, any of that. That's what this linear means. Linearly independent solutions is a completely different thing. That means that that your Wronskian cannot be zero, basically. So don't get those two confused. Now, what this is saying, there exists a fundamental set of solutions for the homogeneous linear nth order of I, any one of them. Okay, now they're talking about, they keep referring to equation 6. You don't have a book with you today.
I can pull up my laptop. Would you like me to?
No, it's all right. I was just going to say what that one is. Remember, the homogeneous means it's equal to 0 in this sense. But the other is all of the a's, the coefficient functions, are only functions of x, okay? And that first one can't be 0 for any value of x in the interval, okay? And the rest of them are whatever. That's what is required. It's just your standard thing, okay? So there does exist a fundamental set for for the homogeneous linear nth order differential equation. Now, here's something that you can think as analogous, okay? You've done enough vector stuff, right, to know what I'm talking about with that, right? You have your x,
Y, and Z.
X, Y, and Z, but the vector here is I, J, and K. Those are linearly independent of each other. You can't come up with any combination of Y, I, and J to come up with a K, or any of the others, because they're completely linearly independent of each other, okay? Same thing here. These functions have to be completely independent of each other. You can't get two of them to make another one, to make one of the others. Then it wouldn't be. Now, here's one more theorem right on top of that one. It starts off the same way here, and I'm just going to go here, this stuff, okay, be a fundamental set of solutions, okay, for this thing, homogeneous, blah, blah, blah. This all goes down here, okay, for that. Then the general solution of the equation on the interval is this. General solution okay, will be this. Y is equal to some linear combination, C1, y sub 1 of x plus C2, yeah, they write them all in, y sub 2 of x plus C3, y sub 3 of x plus dot 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 plus C sub n, y sub n of x. Okay, that is what we call your general solution, where these C's, the C I, when I is going from 1, 2, 3, dot, 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 up to n, okay, are arbitrary constants.
So if we're going to start using like I, J's, and K's, does this mean we're going to start doing three-dimensional planes?
Say this again.
We're going into three-dimensional planes now?
No, these are just, okay. What we have is a differential equation, and it's an nth order differential equation. So that means you're going to have at least n independent solutions to that equation, because it's nth order, okay? And when you combine them and you get this fundamental set that's guaranteed to exist for them, and this is your fundamental set, they're all linearly independent of each other, they don't depend on each other, then your general solution will be, these coefficients here will be arbitrary constants. You can put any constant in there and still have a solution. Okay. Okay. These are your solutions. These things up here are solutions to that nth order differential equation. They are a fundamental set, meaning they're linearly independent of each other. But your general solution, take those and put any constants in you want to in there, and this will always be a solution. Okay? So if, remember that sine of 2 log x over x to the third or whatever that one was, that was independent from the one with the cosine, right? So if those are the two independent solutions for that, then any y, which is any C1 times the first plus any C2 times the second, that's also a solution. That's just saying that any linear combination of those two solutions is going to be a solution. You have an infinite number of solutions. Now, given a an initial value problem that has enough conditions to it, you zoom in on y. But without that, you have an infinite number of possibilities. Okay? Remember when the graphs would show, well, here's a curve, and there's a curve, and here's a curve, and there's a curve, and there's a curve. You have an infinite number of those. And each of those is some linear combination of your fundamental solutions. Y1, Y2. If it's a second order differential equation, it's going to have two. If it's a seventh order differential equation, you're going to have 7 linearly independent solutions. That makes your fundamental set. And then any linear combination of those will also be a solution. You pick any C's that you want. 17, 4, 18, 3, negative 5/3, If those, pick them and put them in there, that's going to be a solution. It means you have an infinite number of solutions, okay? And now, once you have that initial condition, enough initial conditions cover everything, you zoom in and that's your one and only solution, okay? That's what this is saying. They're just saying your general solution is any combination of those linearly independent solutions. Any combination that you want to have, where those constants are arbitrary. Okay. It's a lot of blah, blah, blah. Okay. Hopefully we'll see.
Good example.
What's that?
A good example.
Okay, and I was just going to say, they do a proof here with K's and C1s and things, and they have absolutely no numbers in them. So let's do the example that actually does have numbers. This is example 7, bottom of page 126. Okay. All right, to erase?
Yes, sir.
Okay. Here's two functions. y1 is equal to e to the 3x. y2 is equal to e to the minus 3x. Okay? They tell us that these are both solutions to the homogeneous or homogeneous linear differential equation y double prime minus 9y equals 0 on the interval minus 9y equals 0 on the interval minus infinity to infinity everywhere. Okay, now something I was going to say about it. These are certainly defined everywhere, and there was something else I was going to say about that, but I'm falling the now, so it doesn't really matter. Okay, it's really easy to check. If you take the first root of this, you get the first root of this one.
It's alright. Give me a second. I know is it gonna be chain rule 3e 3x
To the 3x. First root of that one would be
3e to the 3x
minus 3.
minus 3.
Yeah. So derivative of that is minus 3. Okay. Then the second derivative of this would be 9 e to the 3x, and this would be 9 e to the 3x. So minus times minus is plus. So if you have either one of those, they both give second derivatives are going to be 9 e to the either minus 3x or plus 3x. Plug that in here, minus 9 times whatever the one that you had, and that's going to be 0. So certainly those are solutions. Okay? Now the question is, are they linearly independent? Okay? Now, what's a test for linear independence?
You guess. I don't know.
The Wronskian. Okay, the Wronskian of these two functions, e to the 3x and e to the minus 3x. Okay? And you've already done in your head the math formula. You just write these two as the first column, e to the 3x, e to the minus 3x, and then the first derivatives are the second one. What's that?
Oh, sorry. Hey, hold up. Alright, since we're on the subject of I and J,
Okay.
this is exactly the, I know I already said this is the cross product, but if we did y prime and that, does that have any connection? I mean, like,
No, it's just, okay. The use of a determinant is a tool. Think of it like addition. Just because you add two things to get your price of the grocery store doesn't mean when you add something to your meal that you're buying groceries. You're not. I mean, just because you're using addition, it doesn't have anything to do. You use addition there, you use addition here. They could be two completely different things. A determinant is an operation that has multiple uses in lots of different fields. Cross product, it's used very nicely there, okay? But it doesn't have to be used there, but it can be used quite nicely there. When you're solving systems of equations, you can use a determinant. When you're determining whether you have linear independence, you can use a determinant. Determinant is a tool that you can use in this setting or in that setting. And these two settings don't have to have really anything to do with each other. The tool works in both ones. Does that make any sense?
Yes, sir.
Okay. Does that answer your question?
Yes, sir.
Okay, all right. Okay. So what do you put here in the second row?
Oh, it's going to be -3.
Okay, 3x here and minus 3e to the minus 3x there. Okay, and you do the determinant, which is the sort of like a cross product, only different. Okay, you multiply those two together, you get minus 3 minus 3, right? Because e to the 3x times e to the minus 3x, one of those is e to the 3x, the other one is 1 over e to the 3x. That's just 1. So that gives you a minus 3, but then because on the up diagonal, you do the negative, so that's going to be another minus 3. That's equal to minus 6, and that is not equal to 0, so these are linearly independent. Okay? Now, sorry, is it a cold or is it allergies?
It sucks, whatever it is.
It's just aggravating.
I just got it. I mean, I've been stopped up this whole summer.
Right.
And I've been taking some Sudafed this week, and I think it's decongesting.
Right.
And I guess I've been sniffling too much that it's going down here, so that's my fault.
Right.
I was going to go home and drink some hot tea when we get home.
Right. Yeah. All right. So since these are two solutions, we verified they were two solutions. They're linearly independent. The Wronskian tells us that. So therefore, the general solution will be y is equal to any constant C1 times e to the 3x plus any other constant C2 times e to the minus 3x. There's your general solution for that differential equation. Any value C1 and C2 you put in there will give you a solution to that. It has an infinite number of solutions. Okay? That's the general solution for the equation on the interval, and that interval contains everything. Minus infinity to infinity. Okay, let's move to example 8. Okay? Oh boy. This is one of these I really don't care for at all. But we'll do it. Here's a function. Y is equal to 4 times the hyperbolic sine of this is such a bizarre thing, of 3x minus 5e to the minus 3x. Okay. This is the argument for a hyperbolic sine. I wish they'd have put parentheses around it, because the way they wrote it, you can't tell if it's whole expression or not, but I'm pretty sure that's what they mean. They say that function is a solution of the differential equation in example 7, the one we just did. Okay? That is a solution, they claim. They say verify it. This one we really do need to verify. Now this is going to require using some of the rules of differentiation. Oh, you don't have your book.
I can pull it up.
Well, if you want to, you can. You need it plugged in?
No, sir. I charge it this time.
Oh, okay. Do you have in there the inside covers? You have the whole book?
I don't think it covers the inside covers.
Really?
It gives all the chapters, but I don't think it does that. But I'll check.
Okay. Well, I'll tell you what you need if it doesn't. Okay? So what we're going to have to do to verify this, we need to do y prime. Okay? Now, what I'm going to say next, and this is on the inside cover, so it's easily verified. Derivative of hyperbolic sine is hyperbolic cosine. And you do chain rule just like everything else. So this would come up being 12. I don't know where this is coming from. Okay. 12 times the hyperbolic cosine of 3x plus 15 e to the minus 3x. Okay? You okay with that?
Yes, sir. Sorry, I'm using my phone as a hotspot. This Peter has trouble getting on that loss and gets.
Oh, really? Yuck. Okay.
Yeah, I don't see anything on the inside cover.
Okay.
Because it just starts at chapter 1.
Yeah, okay. Sorry about that.
Oh, you're fine.
Yeah. Okay. I'll tell you what you need to know then. As opposed to trigonometric sines and cosines, the hyperbolic sines and cosine, and it's just sort of a made-up name here. There's no such thing. Well, never mind. The difference here, the derivative of hyperbolic cosine is also hyperbolic sine. It's not with a minus sign. So this would be, oops, I left off my x here. Okay. The derivative of that then would be 36 hyperbolic sine of 3x. And then this would be minus 45 e to the minus 3x. Okay. Now, that's your y and y prime. Okay? Now, we need to verify that those are indeed true. Your equation there, differential equation, is y double prime minus 9y is equal to 0. So that is supposed to be true. So let's put it down and see. Y double prime is 36 hyperbolic sine of 3x minus 45 e to the minus 3x, right? Minus 9 times y. Well, here's the y here. So that's minus 36. 9 times 4 is 36. Hyperbolic sine of 3x. And minus 9 times minus 5 is plus 45 e to the minus 3x. And sure enough, that's equal to 0. These two are equal to 0. Those two added equals 0. So that, sure enough, does solve the differential equation. We verified it. Now, what our theorem told us is we have a general solution here. It doesn't look anything like this one. Okay? The general solution was y is equal to c1 e to the 3x plus c2 e to the minus 3x. Now that doesn't look anything like that. Well, maybe a little bit, but not much. But you have to go to what your definition of a hyperbolic sine is, okay? And I don't know that your book anywhere is going to give that to you. I'll just give it to you. Well, a hyperbolic sine is, I'll use 3x since they have. What that is e to the 3x minus e to the minus 3x over 2. That's what hyperbolic sine of 3x is. Okay? So if we had rewritten this problem here, y is equal to 4 times e to the 3x minus e to the minus 3x over 2 minus 5e to the minus 3x. That's just substituting in what hyperbolic sine is. Then, okay, number 1, you see the 2 will go in the 4 twice. So what you have is 2e to the 3x minus 2e to the minus 3x minus 5e to the minus 3x. And this would be 2e to the 3x minus 7e to the minus 3x, and that is indeed a linear combination where C1 is equal to 2 and C3 is equal to minus 7. Okay? So
is basically this whole chapter, we basically try to set constants up?
I haven't quite figured out what the rationale for presenting things this way. We're still in 4.1, okay, and we're still fiddling around with things, and we're not going to be much longer in 4.1. We may not finish it today, but we'll come close.
Well, we're in 4.1. I thought we were in chapter 3.
No, we skipped 3.
Oh, dude.
Okay.
Oops.
That would help. Okay. We get to 4.2, we do some, it's a very short section, but then in 4.3, that's when we start solving these things for good. Rather than, here's a solution to it, verify it. Beginning in 4.3, we're going to be finding our own solutions, which to me is what we should have been doing in the first place. Okay? And 4.4 is another as one way to verify, to solve, and 4.5 is a different way. I think we're just going to do 4.4. I think we're going to do 4.5 because that's just a different approach. So
we're going to go all the way to 4.5?
We're going to skip 4.5. And then maybe we'll get to 4.6, variation of parameters.
Like,
we'll see.
You gave out test 2, right?
Yeah.
And are we going to go to test 3, 4, 5?
No, just test 3, I think.
Okay.
And test 3 will be your last test, which will be your final exam.
Okay, cool. And then paper. Hey, I've attempted the paper today.
What's that?
I got the first paragraph of the paper.
Oh, a good start. Okay. All right. Good deal.
But I'm not done, so
Okay.
I won't have to.
Keep plugging on it. Okay. All right. Let's do example 9. This whole thing here was saying, hey, that's the solution. We verified a solution. Well, our earlier thing said it had to be a linear combination of these two because it was the same differential equation. And all we did was then, by the definition of hyperbolic sine, we saw that is a representation of this, with C1 is equal to 2 and C2 is equal to minus 7. So that did fit the general solution. Okay? And if you just written down what hyperbolic sine was in the first place, it would have been just about intuitively obvious. That's why I don't like using hyperbolic sine. Just write down, this is what it is, this thing right here. Use that instead. It's so much easier to use. Okay, but never mind. All right, let's move to example 9. Okay? Here are some functions. y1 is equal to e to the x. y2 is equal to e to the 2x. y3 is equal to e to the 3x. They claim that these three satisfy the third order differential equation y triple prime minus 6y double prime plus 11y prime minus 6y is equal to 0. Okay? That's their claim. Now, They didn't say verify it, so we'll take their word for it unless you want to verify it. Which you want to do?
Verify?
You want to verify it?
Yeah, I'd like to.
Okay. Not that hard to do. Just maybe a little long, but not hard. Y1 prime would be?
E to the x.
E to the x. You got it. Y2 prime would be?
2e to the 2x.
2e to the 2x, right? Y3 prime would be?
3e
3
to the 3x.
e to the 3x. That was easy enough. Y1 double prime is equal to? Easy.
Sorry, I was listening to that truck.
Oh, I see.
Sorry. E to the x.
E to the x. Y2 double prime is 4 e to the 2x, and y3 double prime is equal to 9 e to the 3x, and y1 triple prime is equal to e to the x. Y2 triple prime is 8e to the 2x, and y3 triple prime is 27e to the 3x. Okay. And if you go back and plug each of those in, let's do the first one. That's going to be pretty easy.
E to the x minus 6e to the
You got to have
x.
an e to the x in every term, right?
Yeah.
So let's just add our coefficients. 1 minus 6.
6, no, 5, negative
Negative 5 plus 11.
6.
Minus 6 is
0.
0. Good deal. Okay. The next one, we would do 8.
Oh, yeah. 8.
And e to the 2x is going to be in there.
8 minus 24 is 16, or negative 16.
Negative 16
Plus 11 is,
plus 22.
plus 22 is, wait, let me restart.
Positive 6. Right?
16.
You say minus 16.
Yeah, positive 6 minus 6. Yeah.
Minus 6 is 0. All right. All right. Let's try this one. Ooh.
27 minus 54 plus 33. Oh, wait, I didn't do that.
No. 27 minus
54
54. Yeah. Plus 33
33
minus 6. Okay, that's the 54. It doesn't look like it, but it is. Okay.
Yeah, that's right. It's
All right.
minus
Because these two add to be
60.
60, and that's minus 60. So, yeah, got it. So we just verified them, didn't we?
Yes, sir.
All right. That wasn't too awfully bad. But what's more, we've got, okay, so now we know those three are solutions. The next question is, are they independent solutions? What's going
Are they?
Okay. How do we check?
We do that C1.
Yeah, the Wronskian. Okay. So if you don't answer right, I'll say wrong.
Wait,
Yeah.
so is the test basically if it equals 0, they're independent?
If they're equal to 0, they're dependent. If the test is not equal to 0, whatever it is, not equal to 0, then it's independent. So the Wronskian of those three, e to the x, e to the 2x, and e to the 3x. This is one reason I didn't object to verifying, because
It made it easier for us.
so it's the top row is e to the x, e to the 2x, and e to the 3x. Second row is?
E to the x, 4e to the 2x.
No, 2e to the 2x.
9e to the 3x.
3e to the 3x.
I looked on sorry.
You skipped one.
Yeah, I looked at one.
Okay. And the third one is?
1 second, please. It's going to be e to the x, 4e to the 2x, and then 9e to the 3x.
Okay, I got an extra e in there somehow.
We're going to go all the way to,
No, you just do those three. Okay? You do to the n minus 1, and which is in this case 2. I did my line too big.
now how are we going to do A, B, C, D?
Okay, now this is what I was going to show you. And I think you'll recognize this from your cross product again. If you had a 3 by 3 cross product, what you do with that is extend the first two and do the same thing. So I'm going to try to shrink a little bit. Okay. I can't get my eraser to come up. There we go. Okay. Now, what I'm going to do here, I want to erase it all, but I'm going to try to not do that. E to the x, e to the x, e to the x, and e to the 2x, 2e to the 2x, and 4e to the 2x. Okay. Now what we do now, this only works for a 3 by 3, so don't get too excited here. Only works for this. We do our down diagonals and multiply those. So that's going to be 2 times 9 is 18. E to the, add those exponents, 6x.
Wait, so we're doing e to the x times 2e to the 2x times 9e to the 3x?
Right.
We multiply all three?
Yeah, multiply the coefficients first, and that gives you 18. And when you multiply e to the x times e to the 2x times e to the 9x, you got same base, e, different exponents, just add the exponents. 3x plus 2x is 5x plus x is 6x. 6x? 6x. 6x? Never mind. Okay? So there's the first one. Do your next down diagonal.
And you get, it's going to be 2e to the 6x.
Wait.
No? Oh, sorry. Let me see that.
Plus 3, right? And that's going to be e to the 6x, right?
Why is it a plus? Because we're going like this?
Because you're going downward, yeah. Down diagonal. Okay? And then this last one would be?
E to the 3x times e to the x times 4e to the 2x.
That's going to be 4 e to the 6x, right? 3x, x, and 2x. Okay? Now those are your 3 down diagonals. Now you subtract your 3 up diagonals. Okay? Minus 2e to the 6x. The next one's going to be a minus 12e to the 6x, right? And then a minus 9e to the 6x.
So your negative numbers equal 23, well, no, that's not 23. It's, yeah, it's 23.
Yeah?
The other one's equal 25.
Yeah. So that's going to be 4e to the 6x, which is not and never will be 0.
Why would it be 4?
Well, didn't you say 25? Oh, no, I'm sorry. 2. Sorry. I was doing 21. 2e to the 2x, 6x, right?
So it's independent.
Yes, that's what it tells you. So all it tells you that those 3 functions are independent of each other because the Wronskian is not 0. Okay? Now, 2e to the 6x, and that's not 0. And that's true for every real value x. There is no x in that domain from negative infinity to positive infinity that will do it.
Now, why when we added the 2 extra columns, why didn't we add a third one?
We didn't need it.
Why?
You're just doing 3 down, and 2 more will get you 3 down, and 3 up. 2 more got you 3 up.
Okay.
You don't need it. Yeah. Now that's just a shorthand. That's a trick. That's. Do you really want to know how you do this otherwise, like a 4 by 4?
You know what? I think I'm good.
Huh?
Do I need to know it?
I don't know if you will or not. If you do, I'll show you. And it works for 3 by 3 too, but it's just a little bizarre, but it's true.
Yeah, we got 3 minutes, so if you can explain it.
Okay. So let me All right, so that did finish. So here's our conclusion. Here's a general solution. Y is equal to C1 e to the x plus C2 e to the 2x plus C3 e to the 3x. And whatever constants you put in there will solve that differential equation as well. Any set of constants will do. Okay. Now, so we'll start next time at 4.1.3. So let me just make a mark there so I'll know to begin there. And we'll start there. Now let me just show you how to do a determinant of what size you want. Just something bigger than 3 by 3. 4 by 4? Is that, yeah, okay. So if you had A, B, C, D, E, F, G, H, I, J, K, and L. Okay, if you're doing the determinant of that, here's what you do. Pick a row or a column, and it really doesn't matter which. Okay? Do you have a favorite there? Row or column?
Row 1.
Row 1? Row 1. Okay, so we're going to go with row 1. So let's start with the A here. Right? So this is going to be, the determinant of that is going to be A. Now what we're going to do is wipe out row 1 and column 1. Oh, wait. This is dumb. It has to be a 3 by 3. Oh, wait, I'm sorry. I erased the wrong thing. Okay. That was D, H, and L. I need 4 rows. M, N, O, and P. Okay. It has to be a square matrix. Has to be a square matrix. So wipe out row 1 and column 1. A times the determinant of F, G, H, J, K, L, N, O, P. Okay? And you know how to do a 3 by 3, expand the first 2 rows and do it like we just said, right?
Yeah.
Okay. All right. Now, we go to the next. You wanted to use row 1, right? Now, here's the little catch with determinants. Okay, now pay attention to this. This is a positional thing. A is a positive position. It always starts positive. And then anywhere you go, right, left, or up and down, not diagonal, right, left, up and down, you change sign. That's a plus, minus, 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 plus, minus. Okay? Now, just a few things to note here. Okay? In this 4 by 4, it just happens to be that all your diagonal elements are plus. No matter what size you have, they're always going to be plus. And the others always alternate. Okay? And if you had said, well, I don't want to go left or right, I want to go up and down. Plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. Anywhere you go, it's always going to follow that pattern. Okay? So, the reason I said that is that whatever your value for B is, it's going to be the minus B times the determinant of what's left then. Okay? So I'm going to erase this mark out and interject this. Erase this column. First row and second column. So then it's the determinant of E, G, oh yeah, if you're going down, E, I, M, G, K, O,
E, G, H, I, K, L, M, O, P.
Okay. Yeah, times that determinant. Okay? If you chose to do the first row, then it's going to be a plus C times what's left when you wipe out its row and column. Okay?
E, I, M, F, J, N, H, L, P.
Okay. E, F, H, is that what you said?
Yeah.
I, J, L, M, N, P. Right. And then the next one would be, and that would, oops, that would be what fit in there, minus D times its remaining.
E, I, M, F, J, N, G, K.
Wait. You're doing D now?
Yeah.
E, oh, you're going down. E, I, M, F, J, N.
G, K, O.
Huh?
Or A, no, G, K, O.
G, K, O, right. Okay. Yeah. So you got it. That's how you do them. So even if it's a 17 by 17, they always have to be square. You just do. Now, there's some tricks you do when you're doing them that'll make things a lot easier. Like if there's some zeros in there, pick the row or the column, either one, that has the most zeros in it. Because when you do a zero times something, you don't have to do that
So
at
you
all.
got y1, y2, y3, y4. You're going to go all the way to the third derivative, so it's a square.
Yeah, right.
So the amount of derivatives you put is based on how many are in the row.
Okay.
Your columns are based on your row.
Okay. Yeah, but here's the other thing. Okay. Where you start that whole process, what's your order of your differential equation? Name an order.
2.
Second order. Then you're only going to have second order differential equation is just going to have 2 possible solutions, right?
Yeah.
So you just you don't do a Wronskian with 2. Well, yeah, you could. You do the function on the top row, first derivative on the next row. So you always do derivatives up to n minus 1. So if it's second order, then you do
n minus 1.
Yeah, you do the function and then the first derivative.
N minus 1, which equals 1, and then 1 minus 0, which is 0. We stop there.
Say that again.
Second order, n minus 1
Is
2
1.
minus 1 equals 1, and then 1 minus 0 can't go.
Okay, well, why do you do a 1 minus 0? Just, okay.
N minus 1s, and your n is going to be 1, because you start off with second order.
Second order.
So 2 minus 1 equals 1.
Okay, so you just do your first derivatives then.
Yeah.
You do your functions in the top row and the first derivatives in the second row. 2 by 2. That's you stop. Okay. That's what you were saying, right?
Yes, sir.
All right, good deal. If you had a 7th order, you do up to the 6th derivatives, you do a 6 by 6. Yeah.
Good.
Yeah.
Good. That's
But we're not going to do those. Yeah. But that's what you would do. All right, good deal. So I guess we're out of time. Yep, past that.